All right, so let's go ahead and continue. In doing a tutorial like this remotely, it's really hard because I don't develop a feel for everyone in the group. Normally, I give people the recursive pi as a starting case, so they don't have to do that first step. But in my mind, that's intellectually the most interesting challenge of this exercise. Without that, it's just exactly the same as I showed you the Fibonacci. And so intellectually, the big step is thinking about how do you decompose a problem into a recursive form. So here's the solution. I always like to start with understanding my base case. What's the computation I'm going to do with the leaves? And what you want to balance is if you make this base case, so I have if n finish minus n start is less than minimum block, that's what decides when I go to my case of what's the computation phase I do with the leaves. If min block is really small, then what I'm going to do is I'm going to fill up my memory with the data structures to hang on to all those tasks and all of the code and all the data space to manage that huge tree of tasks. Notice my base case is huge. And that's just playing around with it. And I'm running on my crappy little laptop. I think if I had a beefy Xeon, I could have a smaller base case. But it's pretty big. I'm not creating a huge number of tasks because on my particular system, it overwhelms fast. So I first write the base case. What's my exit condition? Then I go through and I figure out, okay, how am I going to split this? Okay, we're going to split it in two. And I'm going to have, I pass in a number of iterations, an int start and an int finish. And I'm going to split each of those in two. So that's what I do. I create two tasks and I split it into two. And then I have a task wait and I wait on the outcome and sum them together. And then of course the main is the pattern that now should be very familiar with you, which is I create my team of threads and then I have one thread starts the recursive set of calls. And so that's it. Intellectually, the toughest part, I think, in this exercise is understanding how to take a loop. Because remember, what you started with was a basic loop. So what you had to do was turn that loop into a recursive tree of function calls. So that's with this exercise. Any questions? It's a fun example. I enjoy it. And here's the results I got. It actually worked surprisingly well. So, remember my original program sequentially ran in 1.83 seconds. And, this task case was competitive with my SPMD version. It did really quite well. There tends to be more overhead with tasks. So I usually expect if I can express my algorithm in SPMD, it's going to be better that way than tasks. And you can see maybe it was, but it did quite well, which is cool. So that's tasks. And okay, let me say a little bit more about this. I thought I had a slide about it. When you read the literature read the literature on algorithms, there's this big push, and Charles Leisherson at MIT, who helped write one of the classic books on algorithms, so he has a rather large influence on how we teach algorithms. He talks a lot about cache-oblivious algorithms. Now, I don't know if you've heard that term before, cache-oblivious algorithm. If you write dense linear algebra code, for example, the way you write it is you unroll your loops and block them, and the block sizes are selected around knowledge of the caches. And the more you carry that out, the faster and faster you'll get your code to run, because you want to actually think about what's the size block in the L2 versus what size block in L1. So if you want to get ultimate performance, you literally write the code around the memory hierarchy of your chip. And if you've never written code of this style, you're lucky, and keep it that way. This is not for normal human beings. The term I use at Intel is we call these people ninja programmers, because you basically have to understand the architecture and the memory architecture. But if you're calling a math library and you're calling a dgem in that math library, you probably want people who've written the code that way, because you want them to get a large fraction of peak. Okay, the cache oblivious people say that you never want to write code around a particular memory hierarchy. You want to write your code in a way that it is oblivious to the cache, that it just figures out how to line up around the cache. And what they do is basically what you did in this program here. So this is creating a cache oblivious, even though the Pi program is not sensitive to the cache. But this way of taking a loop and turning it into a recursive function tree, where you break it down smaller and smaller until you get an effective size to compute. This is what people do when they write cache oblivious code. So of course, no one really cares about the Pi program. It's just a funny little toy we play with. But if you have some complex array code and you want it to be portable across different chips, and you don't want to have to worry about the blocking factors for a particular memory hierarchy, this can be a real effective way to write the code. And these tasking approaches have become basically the state of the art in dense linear algebra software. So years ago, shortly after we introduced tasks, the dense linear algebra group, the Flame group at UT Austin, who I consider to be the leading thought leaders in dense linear algebra, they implemented their core libraries around tasks. So it was incredibly powerful, because we first started writing linear algebra where we just parallelized the BLAS, and all the performance came from the BLAS, the basic linear algebra subprograms that we build linear algebra around. You added the second layer of tasks, so pieces of the BLAS that could be run in parallel would just be launched as different tasks, and that sped everything up tremendously. So Robert Van de Gein's group and the Flame team used OpenMP tasks. Jack Donguera, who you had the privilege of hearing talk, I guess, Sunday, he gave the keynote. Gosh, I've thoroughly enjoyed every opportunity to work with Jack. He's a great guy. They created the Parsec runtime, which doesn't use OpenMP because he didn't want to be tied to a particular compiler tool chain. So he built his own tasking scheme, but Parsec is a tasking scheme that does pretty much what you see in front of you. So this tasking approach actually shows up in different guises all over the place. And so it's a good thing to have in your back pocket as a tool to pull out when you have irregular parallelism, and it's something that comes up and is really handy to be able to pull out and use. So that's tasks and divide and conquer. That's really cool. So we have now finished going through what I call the OpenMP Common Core. So I believe, and let's stare at this list and make sure I haven't forgotten anything. I believe we have covered everything on this list. And for the overwhelming majority of anything you're ever going to do in OpenMP, this is enough. There are a few, there's a couple more things in tasks that would be nice to have covered. Someone in the Slack channel mentioned task group. So there's a couple more ways to work with tasks. There's a task loop. So it's another way to create tasks. So there's a few other things that are pretty handy. But really, it's the case that most OpenMP programs, this is all they ever use. And as you glance at this list, and really, let's take a few moments to glance at it, all of this should now be, you look at it and nod your head and go, oh yeah, I know that. So any questions before we go on and go beyond the Common Core? I really want to pause and give everyone a chance to see, do they have questions on this list? And I would look around the room and look you in the eye. Any questions? You know, you create threads of parallel. Those 3 runtime libraries, set thread num, get thread num, get num threads. Yep. Timing. Yep. There are a few more environment variables, but we've only talked about the one that people use all the time, OMP num threads. In fact, people almost never use set thread num. You know, you don't put in your program asking the number of threads. You leave it to the environment running the program. You know how to synchronize now with barrier and critical. That's cool. And you got some work sharing with loop. So I think we got this, right? All right. There's a lot more to the Common Core, and we're going to bounce around and look at some of these things. I mean, the OpenMP 5.0 spec is over 600 pages. It's huge. And they're at 5.2, which has come down a little bit, but the overall specification is just gigantic. There's a lot in there. But what I want to emphasize is think about the design patterns. And I've been on a quest with collaborators at UC Berkeley, and even earlier in my career with the book I wrote on this topic, that to really achieve mastery of parallel programming, you want to learn the key design patterns. And what I do in my book on patterns, which I'm really proud of, the book, I guess, is a little out of date right now, but it covers MPI and OpenMP, but it was written in 2004, so that's before CUDA and the GPU came along. So there's some big things missing from it. But one thing we did in it that I really like is you present a pattern and then you say, okay, here's what it looks like in MPI. Here's what it looks like in OpenMP. And in terms of deep learning of how to reason about parallel algorithms, that's when it really solidifies. So I urge you to think about that. When you think about some parallel algorithm you're looking at, and when you really deeply grok it, then ask yourself, okay, how would I do this in MPI? How would I do this in OpenMP? Could I do this in SYCL? You know, and that's really what brings the deep knowledge that I hope you're after. And so we've talked about fork join. That's, as I said, the essence of multi-threading. If you write pthreads code, it's even called fork and join. So it's very explicit. But you know, OpenMP encourages you to think about forks and forking and fork join pattern. We talked about SPMD. You know, any of you doing MPI, this is mostly what you do. You know, and it's funny, if the MPI people from yesterday were around, they might choke a little bit when I say this. You know, oh, MPI programming is just SPMD. And it's like, well, no, MPI is incredibly general. You can do almost anything you want in it. It's very, very general. This statement is almost everyone working with it just does SPMD, but the MPI standard itself can do more. But you know, this is the Pi program, and yeah, we don't need to keep going there. Loop level parallelism, find your parallel loops, the ones that are time consuming, expose the concurrency by getting rid of the loop carry dependencies, and then exploit the concurrency by adding the directive. So that's pretty straightforward. We love that one. And this is, a lot of people, this is what they think of for OpenMP. And then we talked about divide and conquer, where you think about the leaf condition when you're done, the split, and how you're going to merge. So we just did that one. So there's a huge amount of information on OpenMP if you go to the website. And one thing they've done that I really like is for every specification, and it lags 6 to 18 months, but whenever a specification comes out, they have an examples document. And frankly, most people don't read the specification. The specification is written for compiler writers who are going to implement OpenMP in a compiler. So that's who it's written for. And I'm assuming that most of you don't fall in that category. I know I don't. I am not a compiler person. I learn by examples. And so they have an examples document. Back in my day, because I led the Fortran language committee up through OpenMP 3.1, we had an appendix with examples. But what's happened is that the spec has gotten so large and complex, we now have a separate document. So if you're going to be doing some really serious hardcore OpenMP programming, it really helps to have that examples document for the version you're working with. Of course, I get to plug my book. If you're new to OpenMP, this is the book to start with. Okay, start here. There is Barbara Chapman's book, which is a fine book, but it's now out of date. It's old. So for starting with OpenMP, this is the book to start with. And I think it's brilliant, but then again, you notice my name's on the book, so I am the epitome of biased. But there's another book, and it's older than my book, but it's really, really excellent. And it basically says, you know, Barbara Chapman's book, who Ruud van der Pas helped write too, really focused on everything up to OpenMP 2.5. This book focuses on everything that happened between OpenMP 2.5 and OpenMP 4 or 4.5. So most of the big classes of innovations are covered in this book. And so for those of you who are beyond the, you know, you're not new to OpenMP, you're looking for the next level of detail and discussion of like the SIMD constructs and accelerator constructs, this is the book to get. So, all right, and then of course, other books. So let's go beyond the Common Core. And I'm watching the time closely here because as you can imagine, what I have here is another full day of material. And obviously I'm not going to do a slide race to get through as much as I can. That would be ridiculous. I'm going to go through a few of these through a few of these. And my goal is to finish with the last one about the GPU. But I want to talk about the work share construct. So remember, when we say work sharing in OpenMP, what we're looking at here is a construct that takes a body of work and splits it up between the threads. So that's what we're doing with the work share construct. And the one you've used a lot is for, and the other one you've used a lot is single. So let's come back and look at these in a little more detail. So first off, I want to talk about the schedule clause. So we talked about static and we talked about dynamic, but we really didn't play with them very much. There's another one called guided. And guided, I don't see used very often. But guided is a provably optimal approach for dynamic scheduling. You basically start with a large block, and each time you issue a block, you cut down the size until you get to a minimum size, which is chunk. Hello? A voice came over my computer. It confused me. Okay. So guided, you start big. And what this does is it reduces the overhead. Every time you go back to this shared data structure that holds the work to schedule, you pay a cost. So what guided does is it gives you the advantages of the dynamic schedule, but at the same time reduces how many times you go and check. Then there's this really handy one called runtime. And when you experiment, this is what you do. So you have in your code, you know, pragma OMP parallel for schedule runtime. Compile it and get ready to run it. And now what it's going to do is it's going to look at an environment variable, OMP schedule, that you will pass a string to. And what it will do is it will use that string to populate the schedule. So this is how you quickly try a whole bunch of different schedules. So that's the schedule runtime. Very, very useful. And then there's schedule auto, which, boy, did we argue over that one. My opinion, if you just don't use a schedule clause, you're telling the compiler do what you want. It turns out if you don't use a schedule clause, the compiler will choose one of the existing schedules, static, dynamic, guided, or runtime. Well, static, dynamic, guided. And so they wanted, and we added, a clause which says, no, runtime, do whatever the heck you can think of. We give you total freedom, even if it's something that is not humanly possible to represent an OpenMP, do it, go for it. So that's what schedule auto does. I don't know anyone who does anything too awesome, but too radical, but that's what schedule auto is. So I think I've covered these. And as I said, the one that I use a lot is schedule runtime, because there's times where it's just too hard to deduce from first principles what's the ideal chunk size to use with static or dynamic. And you just want a way to try lots and lots of options. So that's really handy. Now, here's another feature of OpenMP we added pretty early on. So imagine I'm going to do pragma OMP parallel 4. So I'm going to split up a loop. And I have I ranging over 0 to n and j ranging over 0 to m. And imagine n and m just aren't really that big. They're a couple hundred maybe, but they're not huge. What that means is I quickly run out of work to effectively load balance the execution of the program. So we used to, by hand, when we saw a pair of tightly nested loops like this, we used to, by hand, combine them and then re-extract the I and j values for the new combined loop. So we would coalesce the loops. And we were doing it so much, it's like, wait a minute, the compiler should be able to do this. So we added this clause called the collapse clause. And it does exactly what I said. It takes those two loops, loop over I, loop over j, and it combines them into one loop, but instead of ranging over I equals, I less than n, j less than m, it actually will give you one loop over n times m. So if n and m aren't big enough to really give you a lot of work to split up, wow, n times m is. So collapse is really, really valuable. And yes, absolutely, the question in Slack, it will make both I and j private for you. So I can literally write what you see right here, pragma OMP parallel 4 collapse, and I and j will be made private for me. There is no cost and no downside, though, to you calling them private yourself. It's redundant. But for readability, I often do that. So in my code, you might see pragma OMP parallel 4 collapse to private IJ. And it's just there to remind the reader that I and j are private. But yep, that's the way it goes. So this is actually surprisingly useful. All right. So, and here's the next workshare construct, the other one that seems to get used a fair amount, sections. So what this does is pragma OMP parallel to create the threads, and then sections says expect a number of individual section constructs. And each one of these will be packaged up and given to a different thread. So it's very, very coarse-grained. And so, if I had work I wanted to be done on 3 threads, this is how I could do it. And the power of this, you might look at that and go, why don't I just do pragma OMP parallel, ask for 3 threads, and then use the SPMD pattern to say thread ID equals 0 does X, thread ID equals 1 does Y, thread ID equals 2, Z, 2 equals does Z. And that would work. That would work. But there's an attitude in the OpenMP community that, and I don't agree with this, but it's in here, and there are enough people who think this way. I want to have a fairness represent them, that are offended anytime I ask what the thread ID is. And so notice here I accomplish what I can do with the SPMD pattern, but I don't have to ask, what's my thread ID? I don't have to say, are there at least 3 threads? I don't have to ask that. So this will work for any number of threads, 1 thread, 2 threads, 10 threads. This will work just fine. It is a workshare construct. So at the end of sections, you have a barrier implied, but this creates 1 thread to do, I'm sorry, This maps X onto one thread, Y onto another thread, and Z onto another thread. Question in the Slack channel, why would I do this when I could just do tasks? That's a good question. Often when you would use this, it could be done with tasks. But remember, if I have if I have 3 or more threads, I can know that X, Y, and Z are making forward progress at the same time. I can't do that if it's tasks. It's tasks, it's possible X, Y, and Z are sitting in a queue and only one is making progress at a time. So that's where that's where the sections is different than tasks. Now, if there's more than 3 threads, then those other threads just sit and waste time and do nothing. So you would be wasting the other 7 threads, would just be sitting at a barrier going, gee, dude, you should give us something to do, man. You're burning resources. So that's what happens there. Now, there's another little detail that we skipped earlier that I wanted to cover. And this is reductions with array sections. At first, we didn't have this in OpenMP. We added it later, and it turns out to be really quite useful. So in this particular code, I'm doing a reduction across the down each, well, it's row column. So I'm basically doing reductions across the columns to get a reduced value for each row of the matrix. I get row and column mixed up in this, but I'm reducing across the I index and summing it all up into J to give me the summed value for J. So I really want a reduction which returns not a scalar, but it returns an array. So that's what I can do right here. So look at this syntax though. So I initialize my original because it's going to do exactly what the reduction does before. It's going to create the private. It's going to initialize it to the operator plus. It's going to combine the individual sums, and then it will combine it with the original. So notice I had to first initialize the original to 0 so that that combined step at the end would work. And then I have to tell it the size of the array to create. So the syntax is reduction, open parentheses, plus colon A, and then I have bracket 0 to n. So I'm telling it the specific array subsection to replicate. And it'll create a variable of name A, and it's an array, and it acts in every other way just like the regular reduction. This is a fiendishly convenient thing to do. Now, there's a question here about what if n is very large? Excellent point. If n is very, very large, and I do 0 to n like this, I am copying that array into the stack memory of the function that is being run by the thread. So I can easily get stack overflow. So remember, there's a fixed size to the stack when a function is created. So the hazard with reducing over an array is if n gets really large, I can overflow my stack and get ugly, ugly problems. So you have to be really, really careful. And so if n is for good reason really, really large, or if I have a sparse array, so now it's a much more complicated data structure. It's not just going to be a clean, contiguous copy of these bytes. Then I would have to leave it in the heap, and I'd have to use synchronization to make that work. Okay. So, coming back, another question in Slack about not liking thread ID. You hit the reason exactly. There are people who just want to add pragmas. They do not want any semantically meaningful line of code other than the pragmas, because pragmas are ignored if a compiler do not recognize them. And so, yes, that's the motivation for why they never want you to ask the thread ID. Because if I ask the thread ID, I'm calling a library function, and now I've made a change to my program. And if I'm moving back and forth between systems that know OpenMP and compilers that don't know OpenMP, that can actually be really important. So I don't agree with them, but on the other hand, they do have a good reason for disliking the SPMD pattern where I ask for ID. All right, so this is an exercise. We're going to spend maybe 10 minutes because this shouldn't take long. But we've learned about a few extra constructs that you can add to a workshare construct to make them run differently. Go back to your parallel Mandelbrot and thinking about what we just covered. Can you make it run faster? And we're just going to spend no more than 10 minutes on this. So go for it. Think what we covered and see if you can make it go faster. Well, I must be getting tired. I said we'd spend 10 minutes on this, and I forgot what time it was I said that. It's pretty lame, if you ask me. So when you're done, click done. This is one of those where just, you know, it could take anywhere from 5 minutes to 15 minutes. We're not going to take 15. So someone asked what's the advantage of the erased sections with reduce compared to the reduce without? Look, the erased sections is only what you would use if you wanted to reduce and do array. If I wanted, for example, to write a piece of code that looked at a modest sized matrix and summed all of the rows, that's not a scalar. That's where the output of my reduction is a vector. And that's where I'd use the array section, for example. So that's the only advantage. In terms of the exercise we have right now, the focus is collapse, maybe, you know, in going back to that Mandelbrot, maybe a different schedule. Maybe you need the collapse with a different schedule. How does static with the small chunk size compared to dynamic? Does guided help you at all? Maybe if you did that runtime, you could try a whole bunch of different schedules on that loop and see how it would change. You know that num outside variable that's shared that I used the critical on? It'd be better if you passed that in to the loop and maybe did a reduction. I mean, there is a whole bunch of optimizations that you can do with that Mandelbrot. But we're going to go on right now. It's something to play with. And so it's interesting on the Slack channel, someone pointed out that they put collapse 2 on it, but things got slightly worse. Put collapse 2, but then play around with the schedule clause. It's the two of those together where interesting things happen. So remember, the schedule clause is all about balancing the load. The most common case, if you don't do a schedule clause, and the spec doesn't insist on this, but every implementation I know of, if you don't put a schedule clause, what it's going to try and do is divide up the loop iterations into one block per thread and give one block of loop iterations to each thread. Now, if you think about the Mandelbrot set, what makes it such an interesting example to study is you have highly variable work depending on which points happen to fall within the Mandelbrot set and which points happen to fall outside. So you have a case where there's highly variable work from each point in the set, in the space you're exploring to another. So it's definitely a case where getting creative with how the schedule clauses are would benefit you. But if you're going to play around with the schedule clause, you want, for load balancing purposes, you want a lot of iterations to play with. A lot of iterations. Many more than you got threads. So I found when I did a collapse 2 on that loop in the Mandelbrot, I don't think I have a solution here on my slides. Oh, I did. So here's what I did, is I went in there and put a collapse 2. So now, instead of just over endpoints, I'm over the combined loop with endpoints times endpoints. So I just, now I've got, dramatically increased the number of iterations. And then I put schedule runtime, which let me very easily go in and export OMP schedule equals, and I give it a string with the schedule to try. And so the default schedule ran in 0.48 seconds. Remember, this is on my crappy little laptop. Oh, I'm sorry. A wonderful little laptop with an amazing Intel Core i7 processor. Yeah, it's pretty old. Anyway, the default schedule was 0.48 seconds, but the dynamic 100 was 0.39. And then when I did collapse 2 dynamic 100, it went down to 0.34. And there were others I could play with. That's the fun thing with this, with the schedule runtime. You can go through and just dink around and try a whole bunch until you find something that works. And there's a question in the Slack channel that I'm not sure how to answer. I'll think about it and try and type in an answer later. But good question. No, we don't have copy on write type sharing semantics by default. So, and I don't know of a way to force that. All right, so I want to mention just a little bit in this section. So we talked about the critical and the barrier, but there are a couple other constructs I would be remiss if I didn't cover, and I'm just going to cover them quickly. So there's an atomic construct, pragma OMP atomic. Now, I'm sorry, someone had a question I want to answer briefly. How does schedule runtime load balance internally? Keep in mind, schedule runtime just says you take the actual schedule from an environment variable. Okay, so with schedule runtime, all it does is let you pass in the schedule through a string so you can try different schedules. So schedule runtime doesn't tell the system to do anything internally. It just tells it that I'm going to take whatever schedule from this string. Okay, so hopefully that answers that question. Okay, so here's what atomic does. It looks like critical. Pragma OMP atomic, it gives me mutual exclusion. And it says that that operation, X plus equals big ugly B, will only be done by one thread at a time. But it's more subtle than that. It's much more subtle, because actually what it does is this. The atomic only protects the update to the variable X. It's as if you had a temporary where you computed the value of that function. So remember, I have atomic and I have this statement, X plus equals big ugly. It's as if I'm computing that function outside the construct to return a temporary, and then I'm protecting with mutual exclusion just that operation. And you may look at that and go, what a stupidly weird, bizarre thing to do. Now, remember, if big ugly is a simple function that has no side effects, you won't observe any problem with this. No problem. What do you care? But if the function big ugly here does have some side effects, then it can get very ugly, because now you may think you are protecting the function from those side effects by having mutual exclusion, when indeed you're not. We used to say in fact, we said this explicitly in OpenMP 1.0, that pragma OMP atomic could just be replaced by pragma OMP critical for an implementation that didn't implement atomic. And that turns out to not be true, because pragma OMP critical would protect that function. What atomic does is it's tied to low-level hardware instructions. There's a hardware instruction that most, if not all, mainline chips support for doing atomic updates to a variable. And so what atomic says here is connect me to that hardware instruction. And so for simple things like the num outside we just did in Mandelbrot, that might be faster if instead of a critical, I did an atomic. You know, I'm going to a hardware element. So, you know, we would, it could go faster. And, you know, it can be handy. Where atomic is most heavily used, I'm going to say a little bit more than I'll tell you. And later on, we added these other forms of atomics, because it was funny. Early on, it was just this update. But now in OpenMP 3.1, we added the ability to do an atomic read and an atomic write. And the reason we did that is because not all the world is x86. So in the x86 architecture, if your variable fits within a single word, which most of the time for plain old data it does, we automatically, without you asking for it, give you a pragma atomic read, pragma atomic write. But if you're not x86, that's not the case. So if I'm reading from a variable or somewhere else in the program, someone's writing in the variable, I may get a corrupted value when I read it. And so atomic read makes sure that I get a read that's not being conflicted with another write. So, so x86, just to be clear, x86 guarantees, and I have to drop into C++11 language here. The x86 instruction set gives you relaxed atomic read, relaxed atomic write. And what that means is relaxed says, I'm not guaranteeing the order you will see it, but it guarantees that you will only see the read either not happening at all or complete, and you'll only see the write as not happening at all or complete. So that's what relaxed atomics means. And the x86 instruction set gives that to you for free. Now, on one hand, that's really wonderful. That, believe me, that is really, really wonderful. On the other hand, programmers like me who, you know, since the early 90s, basically x86 was my standard chip because I work for Intel. It may be real sloppy because there's, you know, if you're on a chip, if you ever land on a chip that's not x86 and you spent decades working with x86, you're in for a culture shock. So at any rate, that's getting too low detail. So we've added these other atomic operations. There's another thing in the synchronization space. And what we've talked about with barrier and critical is those are collective synchronization operations. They apply across the team. You know, everyone in the team is dealing with the critical. Everyone in the team is dealing with the barrier. What if I want to do something between thread number 0 and thread number 7? It's just a pairwise interaction between a pair of threads. Or what if I want to tie a lock to a data structure? I'm sorry, I want to synchronize access to a data structure, but I want it built into how I process the data structure. So there are things in more nuanced synchronization you can't do with a critical or a barrier. And the most useful, in my opinion, of these is the lock. So a lock, ignore nested locks, truly. Don't even think about nested locks yet, if ever. Let's just think about simple locks, because they're the ones you actually use. So you have a lock type. So it's an actual, you know, object, and you need to initialize that object. And then when you set the lock, you are holding the lock. I set the lock, I'm holding it. Now if someone tries to set that lock, they will wait. All right? And when I'm done, I unset the lock so that I release the lock to someone who's waiting for it. So that's what init lock, set lock, unset lock, and then destroy lock frees it up when I need it later. So here is a simple example of working with locks. Imagine I have two different counters as I'm going to go through this loop. And I'm basically going to look at, in this case, I have a variable of an array of pseudo-random numbers. And just as a crude test, I want to make sure that if I truncate those pseudo-random numbers, I'm going to get an even mixture of same number of evens and the same number of odds. So I seed my pseudo-random number arrays, and I create them between, you know, some number 0 and 50, whatever the number is. And so I have pseudo-random numbers between 0 and 50. I truncate them, and I want to maintain counters for when is it even, when is it odd. And so this is where I'd use the locks to protect those. Now, I wanted to do this with the lock, though, is if I did this with a critical, then everyone's going to lock anytime they update the counter. And that adds a lot of overhead. So it'd be just kind of cleaner if I just said, you know, look, if you're not trying to update the odd lock, why should you be blocked as you're working on the even lock, and vice versa? So this just reduces a little bit of the overhead of managing the locks than if I used a critical. So what I was then going to do is give you this really fun exercise, and we don't have time, so I won't. But what I have is a histogram file. And this is a crude way to test a random number generator. And I don't know you all very well. You know, the fun thing about doing this face-to-face is we get chances to talk during breaks and I find out what you're working on. If you do anything with Monte Carlo type analysis and you don't apply extreme skepticism to every random number generator you touch, you're doing something wrong. You should always test your random number generators, always. So one of the quick and dirty, easy ways to test a random number generator is to create a large array of pseudo-random numbers and then bin them into a histogram. And if you have an unbiased random number generator, you should end up with roughly the same number of values in each bit of the histogram. And so just as a problem to chew on working with locks, I use this histogram program where I'm going to update each bin based on the truncated value of the random number. So, and it can just be awful if I do it this way. So, you know, I truncate my random number, and that gives me, and I truncate the number and by casting it to int, and that'll tell me what bin I'm going to update. And then I'll have pragma O and be critical to put it into that bin. And this serializes, and it's horribly ugly. So here's another way to do it. I have a number of buckets. And so OpenMP and knitlock, I'm going to create an array of buckets. And I don't know why that second, I don't know why that is yellow. Come on, you need to be red. That was weird. Okay. So now what I do is I have a lock for each bin in the histogram. It's as if I'm hanging off of the histogram an array of locks, as if the lock is part of the data structure. So now when I do my truncation to figure out where to put this, which bin to put this in, I now set the lock, but only the lock for that bin. So only if two threads want to increment the same bin will I block each other. If not, then they're uncontended locks and they just scream along and go really fast. So this is where you would use locks, and it's very powerful. It's a critical thing for you to know how to do because it will come up from time to time. It's a little, you know, it's rare. It's not as common as the critical and the barrier, but this is kind of like the next level of detail. All right. So there's another way of doing it. And as long as n bins isn't huge, I can do it with a reduction. So now I'm basically saying each thread has its own copy of the histogram. So do your processing on it separately and then combine them together. And sure enough, that was by far the fastest. You know, what can I say? The critical's awful, much slower than the sequential. Putting a lock per bin is much better than critical, but it's still slower than sequential, which makes sense. There's just lots and lots of overhead. But if I do the replicated array, it's screamingly fast. But of course, if n bins gets really large, I can overflow my stack. Okay, so what I'd like to do now, because I promised I would go there in the program, so I want to talk about GPUs. And I know you have GPU sections coming up. Come on, screen. There we go. And as you see, you have all this other material, um, including a really nice exercise on random number generators, which are really, really is a cool section. But there we go. There we go. Let's talk about this. Programming your GPU with OpenMP. And we are down to our last 15 minutes. So remember earlier, I told you that when you look at the basic stack for OpenMP, that it supports shared address space programming, SMP, which is largely what we've been talking about. There are NUMA features, which we didn't talk about, but, oh well, we can't do everything in a day. And there's a GPU, okay? And I like to stress how much there is in common across these, because, you know, we have CPU cores, SIMD cores, and GPU cores. And notice NVIDIA completely abuses the word core. They don't know, they're misleading you with their terminology around core. Their SMS is it corresponds to a core by any rational computer architecture sense. So I can have GPU cores, CPU cores, I can have SIMD units. And so how do we execute code on a GPU? And a GPU uses, and I personally like this, the NVIDIA created term, single instruction, multiple thread. Even though I don't like the use of the word thread there, but that's life. So the idea is that I have my code, and this is OpenCL code. OpenCL is basically a portable GPU programming language. And I basically write the body of a loop iteration. So if I have some outer iteration range, and here I can cram the body of a loop iteration into a single work item. And then I map that work item over an n-dimensional space. And each instance in that n-dimensional space is an instance of the kernel, and we call it a work item. And I organize them into blocks. And the blocks are the unit of scheduling. They're scheduled in blocks. And then they execute on a GPU. And it's really cool. It's a marvelous way to program. I love it. Now, it's really confusing. And I have an updated version of this slide that's even worse. I have to apologize to you because I'm an old guy who has spent my career trying to support the idea that you as a programmer should be able to walk up to any piece of hardware and pick up your code that you've written and with little to no change run on whatever piece of hardware we hand you. And if you are making changes, it's for optimization, not just to get things to work. And we've done that with clusters. There's not a single cluster in the world that you can't, well, I shouldn't quite be that firm, but almost any HPC cluster in the world, you walk up to it and it will run MPI. Almost any shared memory node that you would find on any cluster, you can walk up to it and you can run OpenMP. You don't have to go, oh, I'm running at Oak Ridge. I can't use OpenMP here. I can only use blah. Oh, I'm going over to NERSC. Oh, they don't run blah or OpenMP. They run schmuck. You know, no, you run OpenMP, and that's the way it should be. And so in 2006, when CUDA came out, about that time, a group of us got together and said, okay, let's create a portable GPU layer. And that's what we did working together. It was called OpenCL. And for a variety of reasons, which would be a long, long anecdote that I'm not going to bore you with right now, OpenCL didn't get off the ground. And NVIDIA said, gee, you guys are going to let us lock you in with a proprietary API? Cool. And they did the smart thing. They ran with it. And so now we have this situation where you walk up to one GPU and it takes CUDA. You walk up to another GPU and it takes OpenCL. You walk up to another GPU and it takes something else. So we've created this disaster for programmers wanting to work with these marvelous devices called GPUs. And the jargon is all over the map. which makes it even harder to use. And the jargon at the level of hardware, the jargon at the level of the programming models, it's really confusing. And I deeply apologize to you because I'm a programming model guy. It's my career to not let this sort of garbage happen, but it did. So you kind of have to, depending on who you talk to, that a work item is the same thing as a CUDA thread. With OpenCL and SYCL, you submit to a command queue, but in CUDA, you submit to a stream. Our index space in OpenCL and SYCL, we call an ND range. In CUDA, they call it a grid. The finest unit of scheduling is organized around thread blocks and work groups. But at the finest scale, it's a work or a subgroup. If you're a little bit confused, you should be. It's just, I'm sorry. We're going to get our act together, but it's taking time, you know. And this is bad because it's been 15 friggin' years since GPU programming showed up, you know. You would think we'd have this all hammered out and worked out in a common standard, but we didn't. Bear with me. So when you're working with a GPU, we think in terms of a host device model, and the GPU is the device. A device is composed of computational units, and at the finest granularity is a processing element. This is the language from OpenCL, but I like it because it's vendor neutral. I map work groups. So a host enqueues a kernel. The kernel runs on a device. Each instance of the kernel runs at a point in the index map or the ND range. The work groups are mapped onto a compute unit. The work items are onto a processing element. That's the mapping. Now let's talk about OpenMP, because that's the basic model. So with OpenMP, you have pragma OMP target. And what that does is it says, take this execution from the host onto the device. So target is how you offload from the host onto a device. And then once I get to that device, I'm now running the initial thread on the device, which corresponds to the code in that block. And as you can see, that code in this block is a pragma OMP parallel 4. So off I run. That initial thread is going to run that pragma OMP parallel 4. Okay, so this transfers control to a single device thread. Now, the memory spaces between the host and the device are distinct. And so we're going to have to talk about how do you move data between the host and the device. And there's a number of issues here, but you have to think in terms of data movement and data that's resident on the host versus data that's resident on the device. So let's start by talking about default data mapping. So in OpenMP, by default, my scalar variables, so if I have int, n, double x declared before the target region, they are implicitly mapped onto a device using first private. So I'm going to map that variable onto the device, and it will be signed the value of the original variable. But when my computation's done, it's not going to copy that back. All right. Now, if I have a fixed size array on the stack, so it's in the memory associated with a function, a fixed size array, it's going to be copied onto the device of the target region when I start the target, at the target construct. And when it's done, it's going to be copied back. So we call this the to from case. So a fixed size array will be copied onto the device automatically by default. And when it's done, it'll copy it back. So that's the implicit data movement. Now it gets a little tricky when I'm dynamically allocating memory off the heap. And this is just a great source of errors. Because I've now created this pointer, and a pointer is just a scalar value, right? It points to an address, but it's just a value. And so the pointer will indeed be copied onto the device where it means nothing. and the data will not be copied. So it would look like this. I have my host thread comes along, it sees a target region. So it's going to generate a target task, which will map the A and B arrays and N onto the device. It's going to run on the device. It has the data A, B, and N to use. And then when it's done, it's going to map A and B back. All right. Hopefully that makes a lot of sense. A question, why do we call this target? Because you think of it that the task on the host is generating and kind of in a control mode, it's generating the work, and the target is the device it's going to. From the perspective of the host, it's who am I going to target with this block of work? And OpenCL is only for C. I do not believe we ever defined it for Fortran. If they did, it was after my time. I worked with OpenCL up through 2.0. I'm in a research organization at Intel. So once the technology is matured, I'm supposed to turn it over to someone else and go on to the next. So I was up with OpenCL through 2.0 and OpenMP through 3.1. Okay, so here's a default case. I create the variables in host memory. I have the pragma target, and so N, A, and B are copied. And then inside, I declared I on the device within the block that's running on the device. So it's private. And then I go ahead and execute on the device, and then I come back. And when I come back at the end of the target region, we copy A and B back. So that's the way it goes. Now we can cover explicit data movement. And this is where I create the target. And on the target command, I can say explicitly map A and B to, and that says on entry to the region, map them on to the device, but it doesn't bring them back at the end. So if I know that I only want A and B one direction, I would use to. From says I want control over who I want back. So from I can use if I want to tell it what variables to map back from the device. And then to from is that case we just gave you, I talked about earlier, where a static array, you map it onto the device, and then when you're done, you bring it back. Now, there are times I want to create workspace on the device, but I don't want to copy something over. And that's where I'll use alloc. I pass in, I say, yeah, create this block of memory on the device. Okay, so there we go. I want to move through these though, because we're running short on time. And so what I've talked about so far is just the target, just getting onto the device from a host. We haven't done anything really that interesting and that GPU-like once we get there. So I need something more. All right, so target gets me onto the device with the initial thread. Teams creates a league of thread teams. And this nomenclature, I didn't come up with this, but think about it. A block of threads is called a team. So what do you call a collection of teams? That's a league. If you think about it, we got, the Seahawks, the Raiders, the 49ers, each of those are teams, and you put them together, what do you have? You have the NFL, which is a league. So the teams construct creates a league of teams. And you're going to basically have one per compute unit. The distribute construct kind of works like the for construct. And it will, oh yeah, we're a bowling team. It works kind of like the for construct. It'll take loop iterations and it will distribute them onto the initial threads of each member of the league. All right? And just like the for loop, I can have these different kinds of schedules. So what we usually get, and let me try and get through this. Okay. So what you usually do is you have the loop you want to map, and you have pragma OMP target, pragma OMP teams distribute, pragma OMP parallel for. Or what you will often do is have a combined construct, which is pragma OMP target teams distribute parallel for SIMD. I call it the big ugly construct. So let me explain this, and then we'll talk about an actual program using the big ugly construct. So with OpenMP, we have a target construct to get on the device. We have teams distribute to distribute the work basically onto each compute unit. And then we have parallel for SIMD to break the work up onto the individual processing elements. And we have the combined construct, which is pragma OMP target teams distribute parallel for SIMD. So I want to walk through an example real quickly, and we're out of time. So I'm just going to talk through this, and you can study it more closely on your own. I'm going to do a Jacobi solver. Now, typically when people look at a Jacobi solver, it's a relaxation solver, a relaxation method. And the standard method people use is a heat diffusion equation. And what I don't like about that approach is you have no way of knowing if your answer is right. You eyeball it, and that's not satisfying. So instead, I derived a Jacobi relaxation solver that solves AX equals B. So imagine I have an array A, and I can break it into a lower triangular, a diagonal, and an upper triangular matrix. And so I can do the math and multiply through X, and I can solve to get that X equals that expression, B minus L plus U over X over D. So now I can just iterate through so that the new value equals that expression above for X with the old value of X. And so I iterate. And so this gives me a way to do a relaxation method across a mesh, but when I'm done, I can then multiply my solution by A and compare to B to see if I got the right answer. Really cool. I'm really proud of this. It's cool. And I thought it up. I did this myself. Maybe you can look it up, but I derived this and did it all myself. And it's really cool. The disadvantage is it takes a hell of a lot of iterations, and it only works for diagonally dominant matrices. You know, there are much better algorithms, relaxation algorithms for doing this, but they're harder to parallelize. So here's what it looks like. So I have, while I'm not converged, so I'm going to keep going until I converge to less than my maximum iterations. And this is basically the same as I did on the last slide. It's the code version of what I've described on the last slide. And so we iterate until our error term is small. And so this is what it looks like. Pragma OMP target map. So I got the maps there for getting the data on. Pragma OMP teams distribute parallel for SIMD private. So there's my big ugly directive. Okay. So it worked. That's all I added. And I got a result. And the performance was really, really ugly. 131.94 seconds. So I did, two different kernels. I did a kernel for the basic iteration and a separate kernel launch for the convergence test. And it took 131.94 seconds. Okay, what's going on? Well, I'll tell you what's going on. I did this map every time I entered the target. And if you just count it up, this takes on the order of 4,000 iterations. And each iteration, I'm doing 3 times ndim plus ndim squared times size of type bytes. And I forget off the top of my head, but that adds up to an awful lot of data movement. And then I'm going to do that again as I come out of each of the target regions. So it's really ugly. So what we have is something called the target data construct, which gives me more fine-grained control over exactly when I do the data movement. So now I do the movement once at the top of my block of code. Then I do the pragma OMP target for the solve, my pragma OMP target for the convergence test, and I only do the data copies, entering those blocks and exiting. Does that make sense? And so it's like the new thing here is the pragma OMP target data. Because the essence of working with the GPU is you have to manage very, very tightly your data movement. You have to. And so this is what it looks like in the code. And you can see I went from 131 seconds to 18.37 seconds. So it made a huge difference. There's another thing with GPUs I need to mention. If you're new to GPUs, this is something that takes some getting used to. And the GPU vendors try and be a little bit quiet like this. This is why we like to call each independent item a work item. NVIDIA calls them threads. And you see, threads do a really good job of if one thread's busy, the other threads just go on and everything's fine. But when you actually look at the architecture of a modern GPU, at the innermost execution processing elements, there's SIMD arrays. They're arrays of SIMD elements. That's how they get the power. That's how they get the efficiency in a throughput mode. So all of those elements in a warp or a subgroup execute almost in lockstep. They're all doing an add, and they all do the minus, then they all do the times, and they all do this operation. And they all do it together, one by one by one. So you think in terms of a processing element as a lane of a SIMD unit. In fact, hardware architects, that's the generic term they use to refer to the hardware element at the finest granularity in a GPU. It's a SIMD lane. So imagine you have branchy code. What do? Well, everyone starts, they're doing their work. And then, you know, if you have a branch, the guy who takes the branch executes and everyone else no ops. You have the second branch, okay, someone does that, everyone else does a no op, so forth. And then after all the branchy stuff is done, you get converged again, and then everyone gets back into converged execution flow. So branches just mess things up. And so what you do when you work with GPU code is you try and eliminate branches. So if I have, for example, if A is greater than B, do this, what I do instead is I always evaluate the expression, but then I mask its application. So here I have an operation where I accumulate it, I add it in only if A is greater than B. So what do? I compute that term A minus BC always, but then I check a mask. Well, if A is greater than B, then the mask is 1. Otherwise, the mask is 0. So now I can just mask times temp, so I'm only accumulating into the set for which the mask was satisfied. So I got rid of the branch. All right. The other thing, and I did 2 optimizations here, which is good because I'm out of time. The other thing is you want to coalesce your memory. And what this basically says, I have all these examples here you can look at, but what it basically says is if work item I accesses memory location, a given memory location, say n, then thread I plus 1 should access the memory location n plus 1, okay? And it's just, there still are caches, there's still blocks of memory you're moving around. And so you want to make sure that of the SIMD lanes in a unit, that the memory lines up across the SIMD lanes and that you're not doing scatter and gather as you move operations around. So memory coalescence is when you organize your memory accesses so that they line up across the SIMD lanes of your innermost execution units. So when I do that, and I talk about it in more detail here, I get my execution down to 7.64 seconds. Now, the power of what I just did, though, is what I just told you is remarkably complete. Oh, I mean, we can go on and talk about GPU algorithms, and there's a lot to do. But at a high level, I've just shown you what you do in GPU programming. You find a loop, you take the body of the loop that you're going to map onto the GPU. You then think really hard about data movement, and you manage your data movement explicitly. So you do no more data movement than you have to. Then you get rid of divergent execution flows. You don't want branchy code. GPU code with branches just sucks. You get rid of branches, and then you think about your memory layout so that you have this, coalesced memory layout. And that's it, really, that's it. You're now GPU programmers. Well, if we had a whole day on GPU programming with OpenMP, and I have a tutorial at Supercomputing where we'll do a whole day on just walking you through this in the same style of what we've been doing all day, with the learning by execution. At any rate, if you want to learn more about OpenMP for a GPU, they have a chapter that covers this in this book. And right now, that's the best place to go. I'm working on a book right now with Tom Deacon at Bristol University. We're about another year. We hope to have it ready by this fall, but life gets in the way. So by next year, about this time next year, I'm hoping we're finishing a book. We're an entire book about programming your GPU with OpenMP. I want to say that anything I can do in OpenACC, I can do in OpenMP. The difference is OpenACC is not an open standard, and OpenMP is. And part of the reason we're in such a mess with GPUs is that people don't demand open standards, so you don't get them. That's really what it is. Every time you use CUDA, every time you use OpenACC, you are rewarding non-open standards and bad behavior. And so just don't do it. And this is why the talk later on this week about SYCL is so important, as it's another open standard for programming GPUs. So that's it. And I'm 10 minutes late because I was supposed to stop at 10:45. Is there an option for async data movement with OpenMP? There is. It's not easy. But you can do it. You can do it. The GPU world, I just have to say, it's frustrating and fascinating, and I love it. I'm an anomaly at Intel, and that I've been begging for good GPUs from Intel for well over a decade because I like them. I tease NVIDIA a lot, and they do a lot of things that piss me off, but I have to say, they build really nice devices. Their GPUs are remarkable. And what's fascinating to me is if you look at the future, I happen to know what Intel's doing in their CPUs, and many things I can't tell you. And I happen to know because I follow it very, very closely. I have really good ideas what NVIDIA is doing inside their GPUs. And when I look at them purely from a hardware architecture point of view, what's fascinating to me is CPUs are becoming more and more GPU-like, and GPUs are becoming more and more CPU-like. And it's funny. I wonder how these trends are going to continue to unfold. Maybe the day will come 10 years from now when, we look at a GPU and it ain't that different than a CPU. And we look at a CPU and it ain't that different than a GPU, and they reconverge. I don't know. That's going to be fascinating. But NVIDIA has done something utterly magical. And I want to just sing the praises of NVIDIA because they have figured out how to have individual program counters per CUDA thread, which allows them to diminish the impact of divergent execution flow. It's brilliant. From a hardware architecture point of view, I do not know how they could do that. It's really brilliant. So yeah, bravo NVIDIA. They do some, they piss me off on the software front with their non-treatment of standards, and marketing at NVIDIA is just wrong, but they're a good company and they really build some fine hardware. So yeah, there's a question here, from a developer's perspective, GPU programming is very confusing. It is. It bothers me, and today, it's difficult to know if there's a single language standard to use. Yes, it is. You can use OpenMP everywhere, but the problem is not all compilers support it well. So when I teach this course, I usually use the Cray compiler for OpenMP because it has the best GPU support I know of. And I run it on NVIDIA hardware because it has the best support with the Cray compiler. It's a mess. Now, Intel's OpenMP compiler is in good shape, but we're not shipping in volume our GPUs that work well with it. And yes, you can use the OpenMP GPU to leverage GPU local memory. I haven't talked about that, but you can, you have to. So it is frustrating. I can definitely see where someone sits there and looks at this and goes, oh my God, how am I supposed to deal with this GPU world? You can use CUDA, which is a very well-designed language, but then of course, you're locked into NVIDIA. And vendor lock-in is always bad, always bad. This is why the COCOS talk, which I guess is coming tomorrow, you know, it's the developer community taking control into their own hands and saying, we're going to define this restricted pattern, and then we're going to map onto the back ends, but we're going to save our developer from having to pick. So that's a good strategy, but now you're dependent on the COCOS people mapping onto the GPU you like. So at any rate, yes, it is frustrating. I don't know what to tell you. You know, CUDA is a wonderful language, but we have to stop using CUDA. And SYCL's great for C++ program. It runs everywhere. It's, I think, a great option for C++ programmers. For C and Fortran programmers, really your only choice as an open standard is OpenMP, but its support isn't universally good yet. And that makes it a difficult choice. So I just have to say the state of GPU programming is understandably frustrating right now. And I'm sorry about that. I'm a failure. Okay, we've come to the end of our time together. I thank you all for sticking with me to the bitter end. And I can hang out for a little while if there's specific questions, but you got to be tired. It's 5 o'clock your time on the East Coast time.